Hello everyone and welcome back to this next lecture. So in the previous lecture, we had plotted the output voltage vectors, a few sample output voltage vectors, required output voltage vectors rather, and we had seen that they have a counterclockwise direction movement as the phase angle increase, and the phase angle will increase as time increases. So this means that we have to move in the same counterclockwise direction with respect to choosing our switching combinations for producing the converter output voltage vectors. Now in this lecture, and we had also seen, before we go to this lecture, we had also seen that it is possible to have a rectangular approximation to the three-phase output voltage, and that is by choosing one entire switching combination for this region that is a bisection between two vectors. So for example, between RV4, if the output voltage vector is anything between RV4 and RV2, we can approximate it by this converter voltage vector V4, which is this particular switching combination. That's what it means. And this is as time increases and as the required output voltage vector moves in the counterclockwise direction throughout this 360-degree plane, the voltage vector switching combinations will change. Alright, and we will also move in the counterclockwise direction, and we will choose for the similar time intervals other converter voltage vectors. Right? So in this lecture, we will talk about how we can achieve pulse width modulation to create an approximation of this output voltage vector using these switching combinations. So again, these are our converter voltage vectors, the ones which we have marked as V1 to V5, V1 to V6. These are the converter output voltage vectors. Using these converter output voltage vectors, we have to now come as close as possible to our required output voltage vectors. This is our challenge. Now, to be able to solve this challenge, I'm going to go back to the previous simulation and look at the gating signals. We did not look at the gating signals. Let's look at the gating signals. So for this, we have to start our circuit simulator. Let me go over to the command line and let me open a new tab. So as always, this is the base environment. So let's first activate the circuit sim environment. We cannot activate the SP environment again because we now have to use the circuit simulator. And let us go to the home directory. Let us go to downloads. This is where the circuit simulator files were. Go to simulator interface, keep changing directory until we come to manage.py. This is our root administrator file. And let us launch our circuit simulator. And the circuit simulator is running as usual. Let us copy this link. Go over to our web browser. Open a new tab. Paste it. And we can go to our simulation library. We don't need to create a new one. Remember, we had already simulated it. So this is the last one we simulated. Three-phase converter with basic PWM. So let us load the simulation. Right? So all we have to do is go over to this last view output page. Right? And here we may need to make some changes. Well, let's go back and have a look at our control output interface because we need the gating signals. So let's see what gating signals we have. So let's come all the way down here. And we do not have any gating signals. So we have to add them. So let me go over to my editor and let me open up the previous one. That is basic PWM. And within basic PWM, let us pick out the pwm.py file. Right? So in this pwm.py file, we have to now start creating plot. That is variables that we want to plot. So I will call this PWM S1 gate and let me create them. Now I don't want to go and create all 6 of them, right? We don't need all 6 because we know that the state of the lower devices is complementary to the state of the upper devices. So if the upper devices are conducting, the lower devices cannot conduct, and vice versa. So let us just plot S1, S3 and S5. So we'll get a slightly cleaner plot, right? So PWM S3 gate is equal to, and PWM S5 gate is equal to. So these are all the upper devices. That's all we are looking at. So let's come up here and copy. We shall copy S1 gate, paste it, S3 gate, paste it, and S5 gate, not S6 gate, S5 gate, because we want only the upper devices. And we can get the modulation signals as well. Alright. Now, I'm not going to plot it because I'll tell you we don't need it. I want to explain something else to you. If you want, go ahead and plot it. If you want to verify for yourself that the gate signals happen at the intersections. But we've already seen it so many times before. There's no time to do it again. No need to do it again. What I will do is I will create these variables. So let us add a variable storage element. And change the status to yes, initial value is 0. Let's come back here, copy it, and come over to the web browser, paste it. And let us create 2 more. Come down here, say yes. Initial value 0. I can actually just paste it and change this to S3 gate. That will be just easier. Save it. Come down here. Create the last one. Come down here. The usual. Change it to yes. Initial value 0. Paste it and make sure you change this to S5 gate. So I will change, save it. Come down here and just have a look, make sure it's all okay. PWM S1 gate, S3 gate, S5 gate. That all looks okay. So let's come up here, and as always, whenever you make any changes, export control. Right? Now, come down here, go back to the main page, and we have to run this program again. Because remember, we've created new variables, and these variables will not automatically, the old output data file does not have it. So we must run it. So let's run it. Okay, simulation is running, but like I said, always go to the command line and verify that there is no unexpected error. So it is running indeed, so it's good to know. Let's come over here and let's add a plot. So I'm going to add the plot, and I'm going to call this PWM, because that's what we are looking at. We are looking at the PWM gating signals. Okay, let's come down here and let us add first the carrier waveform, call it C. Save the waveform. Then I will add S1 gate. Sorry, I added it again. Add it and call it S1. Save the waveform. Add S3 gate. Save the waveform. And add S5 gate. Save the waveform. So we have information of all 3 legs, because even if these devices are on or off, we can automatically figure out that the other device is also complementary to it, right? So we will see that very soon. And we can come over here and we can just export to Matplotlib. Let's go over to our editor. Again, export, look at the files, and we want autoplot.py. Alright, so we've already seen the other graphs. I'm just going to comment all of them along with these font lines. So let's get rid of all these. These are the ones we need. So I'm going to stop here and toggle line comment. So this gets rid of all the old plots. This is just to reduce the amount of time it takes to create a plot. So let me go over, create a new tab again. And again, we have to go back to the home directory, go to documents, switching strategies, then 3-phase, and let's see what's there. Then there's basic PWM, and this is the autoplot.py file. Again, we are in the base environment, that's not enough. So we must activate SP. SP is good enough for creating plots. We don't need the circuit sim again. So let's clear this and let us say python autoplot.py. And I forgot to tell you, but just in case you're wondering, you can have as many terminals open as possible, and you can activate any environment as many times as possible. So we have the SP environment open in this terminal and also in the first terminal, and that's perfectly okay. This is not a violation, nor does it really cause any great burden to the system. It's not a big deal at all. So you can have as many plots as possible if you want to compare plots. So now let us expand this and let's go all the way in the beginning and have a look. Alright, so we will now go and expand. Let's expand on some interesting part. Let's not expand right here because usually things happen here. So let me go and expand here. So I'm going to pick out one carrier cycle. Alright, so starting, let me zoom in a little more because I see we picked up a little more. So this is one carrier cycle. That is, we are starting scrutinizing at -1 and we end again at -1 of the carrier waveform. So this is one complete cycle of the carrier waveform. Now let's take a look at what's happening here. The blue line is the carrier waveform. That's pretty obvious. There is a yellow or orange line. Again, I don't know if I'm colorblind or whether I just can't make out what it is, but this yellow or orange line is the gating signal for S1, which is the upper device in leg A, or the first leg. The green one is the switching signal, is the switching for S3, and the red one is the switching for S5. Alright, so if you take a good look here, you'll see a few fairly interesting observations. Actually, let me try to get as close as possible to this. Okay, so this is a little clearer. So you see here, it's actually quite interesting, right? Now, look at what is happening. First and foremost, a few things. This here is the central line of the carrier waveform, right? You draw a vertical line through this peak of 1, you will get the center of this carrier waveform. So this is one half, this is one half, right? Of this one half cycle and another half cycle. Now, if you look at this, you will see that the switching in this left half is exactly symmetrical to this right half. So it almost appears like they are mirror images of each other. You can actually fold them, right? If you imagine this as a piece of paper, you can fold it and they will exactly overlap, right? Go ahead and think for a minute and you'll find that this is indeed the case. I hope you are also checking this out with me on your own circuit simulator, and you can verify for this for yourself. Now look at what's happening. At the beginning of this cycle, all three devices are on, right? This only means, okay, actually, again, mistake here. I should probably give them a magnifying factor because they are overlapping. My bad. Let me come here. S1 can be the same. Let us change S5 to by 5% and let us make S3 by 10%. Right? Just so that we can actually see all of them independently rather than them merging together the way they are right now. Alright, we have to do some zooming again, but that's not too bad. So let us zoom. And let us zoom again here, like I said, somewhere in the middle. This one looks interesting. Now let me go a little more. I just want a place where you can actually see some interesting shapes so that we can actually make out what's going on. Okay, so you see here something interesting is happening. All of them seem to have some interesting stuff. So let's go zoom in here. Let's figure out what's happening. So I will zoom in and eventually I want to break this down to one cycle. So let me go pick on this cycle here. Again, I would have liked this one, so that's why I'm trying to grab it. But anyway, let me go back here again and let me pick on a few cycles here. So let me go pick on a few cycles and then zoom in. All right, here, let's look at this. This is an interesting part. So let's go a little here so that I get the entire cycle. That's very nice. And a little more. So we are back to the same old. That is, we now are starting from -1 to 1. We've again captured one cycle. And again, you can do the same as usual. It is still symmetrical. Draw a vertical line passing through this 1, right? And you will see that the left half and the right half are symmetrical. You can actually flip them and you get exactly the same, right? Imagine them to be a piece of paper, fold it, and these, the left half and the right half, will exactly align. So let's look at what's happening on the beginning. If you look at the beginning, all of them, right? That is, all three upper devices are conducting. All right, verify for yourself. S5 is the red line. It is 1, which means the upper device in leg C is conducting. The green is also 1. They are just magnified, but they are all 1, which means upper device in leg B is also conducting. And the yellow line is also 1, which means upper device in leg A is also conducting. All three upper devices are conducting. What does that mean? It means that this, up till here, the first part, it is 0. All right, which means until this instant when device S5 starts getting turned off. So here, see here, device S5 starts getting turned off, which means device X6 will turn on. Remember, always the upper and lower devices in a leg are complementary, which means if S5 is turning off, S6 will be turning on. I just didn't want to put it here because then there'll be too many devices and you won't know what is what. Okay, that's all. But you have to imagine this. At this point here, now there is a switching combination. What does that mean? At this point, you have the combination that is S1 is high, S1 is on, S3 is on, but S6 is on. Alright, S6 is on. Now, if you're wondering what that is, let's go over to this first one and let's plot this also. Alright, so now we have two plots. So let's place them next to each other. Let's place them next to each other like this, right? So which means if at this point I have this combination, that is S1 is high, right? So I have 1 for the first leg, 1 for the second leg, and 0 for the third leg. Remember, if S5 is turned off, that means the position, the pole status is 0. The pole voltage will be 0. S6 is conducting. But 110, what does that mean? Come over here and have a look. 110 is vector 6. It is this vector which is being applied. Alright, it is this vector which is being applied. That changes when S1 also turns off. Right? Remember, S1 is turning off at this instant. S5 turned off a little before. When S1 turns off, then our state is 0, 1, 0. Why? Because in the first leg, the lower device is conducting. That pole status is 0. In the second leg, the upper device is conducting. That pole status is 1. Third leg, the lower device is conducting. Again, pole status is 0. 0, 1, 0 corresponds to V2. Alright? And then if you come here, you'll see something else. You will see at this point, for the rest of the cycle, it is all V2. So here, for a short period of time, we are applying the V6 vector. So initially, it is the 7th vector, V7, which means all are on. Then we go to V6. That means between this red line and the yellow line, we are applying vector V6. And for the rest of the cycle, we are applying vector V2. Near the midpoint, something very interesting happens. S3 also goes to 0. Right? S3 also goes to 0. What that means is now it is 0, 0, 0. That is this 0 vector sitting right here. Right? So, and again it flips around. So what happens in the beginning, we start with V7. we go to V6, we go to V2, and then we go to V0. And again we repeat the process. V0, V2, V6 and V7. I would urge you, please pause the video right now, right? Pause this video, figure this out for yourself. If you do not have the circuit simulator running, please run the circuit simulator, get this same close-up video, close-up plot that I've got, and please verify this for yourself. You can even verify it for any other switching cycle. That's also okay. This would be applicable to pretty much any cycle. All right. Now, what are the inferences we can draw from all this? All right. There are several inferences. We are doing basic PWM, right? Now, in basic PWM, we were actually giving 3 different modulation signals to 3 different converter legs, performing sine triangle modulation, getting our gating signals. But really speaking, it appears like as if we are actually applying the converter voltages also. We are indeed applying the converter voltage, except that we are not directly applying them. We are applying them indirectly. We are generating the gating signals and then we are inferring which are the converter voltages which are being applied, right? But what is important is now we can reverse engineer it. This is what is happening over a cycle. All we have to do is reverse engineer this. Now you might say, what is the purpose if you want to come back to the same thing? But really speaking, there are a couple of advantages that you can feel with this. And let me zoom in here for a minute. Number 1, our switching signals are symmetrical over the entire switching cycle. Now that's a good thing, right? That's a good thing because we want to apply a certain voltage. That is, we want to apply a certain voltage in the A phase, in the B phase and the C phase. And the objective of this is to produce certain currents or to produce a certain 3-phase output voltage, right? And we want the average value of our 3-phase output voltage to be a certain value over the entire cycle. So if I were to calculate the average of this 3-phase output voltage, we can do this for the A phase, the B phase and the C phase separately. Alright, so I can say that the A phase, which is S1, it is on for a certain period of time and it is off for the rest of the time. So which means the average A voltage will be equal to the DC bus voltage multiplied by the time for which the upper device is on, S1, right? That is this period. And the same we can do for the others as well. And once we have this average voltage, we can then calculate our 3-phase voltages. Alright, this is what we can do. But by having symmetry over the half cycle, this ensures that what we produce here will always have a kind of, how would you call it? It is an equalizing effect over an entire switching cycle. Which means this. If we want the current to increase in a particular phase, right? Then of course, when the device, supposing we want, let's say for example, we want the current in phase A to increase. What that means is, we will turn on device S1. And if device S1 is turned off, the current will increase, right? The current will increase and the current will then fall when the device is turned off. Now, you could then bring both on times together as one continuous on time. So this on time here at the end of the cycle can be brought and joined somewhere here, right? You would still get the same on time. You would still get the same average output voltage. That does not change because remember, the average is merely the on time of the upper device multiplied by VDC, multiplied by the VDC. Because remember, we are taking the average voltage. So that's not changing. But then in that case, the ripple will be completely concentrated in this first half of the switching cycle. And after that, it will completely fall. This results in a kind of a asymmetrical ripple, which is not very nice in an AC circuit, right? In an AC circuit, you would like something smooth and also which is symmetrical in both the positive and negative half cycles. That is also very important because remember, if you produce something which is asymmetrical, between the positive half cycle and the negative half cycle, you may end up with a DC offset. You do not want to be injecting DC into an AC system. Alright, so therefore it is a good idea to split your on times into two parts. Alright, that is, you want a certain on time, divide it into two parts, put it in the beginning and put it in the end. Or put it wherever you want, but split it into two parts and make your thing symmetrical. Now, the rise in current, it will rise for a certain amount of time, it will fall for a certain amount of time, but then it will rise again towards the end of the cycle. This results in a much more symmetrical current waveform, which is better for an AC system. So, this points us to several very interesting phenomena, right? Now, let us suppose we want this same pulse width modulation waveform, this similar type of waveform, except that we want to keep our coordinated strategy, right? Why? Because remember, even though we are getting something similar using sine triangle PWM, the disadvantage of sine triangle PWM is that as your current rating increases, as your voltage rating increases, you may not be able to guarantee the maximum. That is, you can't always guarantee that things will be like this, because remember, your modulation signal is coming from a control output, and if it is coming from a control output, there can always be displacements, right? These, because remember, this is all due to comparison between modulation signals and a triangular waveform, and this can be displaced as the system becomes more uncertain. Therefore, in a real system with harmonics and with other non-idealities, this could face some fluctuations. And when that means, when you have such kind of fluctuations, then in that case, you can't guarantee that you are using all your voltage levels in an optimal manner, right? So therefore, this strategy is still better. This coordinated strategy is still better. But for us to be able to apply pulse width modulation, we need to do something similar the way it has been done in this sine triangle method. And in the next lecture, I'm going to start listing out what those are. Alright, and these are going to form the basis of our strategy which we are going to implement as space vector modulation. Right, so we are coming closer. Right, we just said first that we need pulse width modulation. We like this coordinated strategy because now we have full control over the converter. Right, we are not doing something independent over three legs. We are applying gating signals to all three legs simultaneously, which is a good thing because now we have full control. But even though we have full control, we still need a waveform, or rather a switched waveform such as the one we got with sine triangle PWM. Only then can we guarantee that we have pulse width modulation, and that pulse width modulation is what we need to ensure that our switching frequency, our waveform, or rather the Fourier analysis or the frequency analysis of the output voltage waveform of the converter will have high frequency components in the carrier frequency range, which can be filtered out conveniently. This is important. If we have some other strategy which is non-ideal, we can't guarantee. We may end up with some other kind of frequencies, and those frequencies may not be that easy to remove. So, with this, I'm going to end this lecture. In the next lecture, we will start talking about a strategy and merge the bridge, or rather cross this bridge between sine triangle PWM, or rather we'll actually be crossing back and forth several times, but we will use this sine triangle based PWM to generate our space vector PWM approach. So once again, if you have any doubts, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture. Thank you so much for listening and see you soon. Goodbye for now.